next speaker is Shinsei Ryu.
Thank you very much for the invitation to this great meeting. Today I'm going to talk about some sort of, if you wish, is kind of tool or knobs to study quantum many-body systems. I will focus on one special dimension for today. So I will start with just quantum mechanics. It's a UQM meeting, so I start with QM, but just for now it's quantum mechanics, not quantum material yet. Okay, so what is the most fundamental thing in quantum mechanics? At least one of the most fundamental things in quantum mechanics is the inner product. And then we use it for all times, and then we compute transition amplitude, or we compute expectation value, and so on and so forth. And then as the title suggests, we want to play with this concept of inner product and try to make it ultra quantum eventually. So it is kind of convenient to think this more in terms of entanglement, maybe just for my personal taste, but I think there's some interesting connection. So think about the quantum entanglement as a kind of way to contract quantum state. So take some highly maximally, let's say, entangled quantum state. Then you can sort of feed the two states into this the entangled state. And then, in fact, it turns out to be just the inner product. And then here, the example could be, of course, the bare states, which is just a state for two spin 1/2 degrees of freedom. But we could do this for more generic setting in many-body quantum physics. It would be also convenient to use diagrams to understand what's going on. So in a product, you just have a sort of perfect channel where you input state from the bottom, and then on the top there's another state waiting, and then we basically just contract index, and that is the inner product. To make a contract with quantum entanglement, we can basically bend this part of the diagram to make everything living in the ket space or Bra space. Okay? So then now you can feed two states from the top, and then that also contracts the index, and then that defines a inner product. And then we can also think this in terms of a geometry where we have like two, so to speak, wormhole. There are two regions in space-time, and they are connected by wormhole. And then this region is, in fact, it is basically represent quantum mechanically the quantum entanglement state. So it's known as in the slogan of ER equal to EPR. Okay. So following this line, we may be interested in generalizing these things into more interesting geometries. For example, we could consider geometry with multi-boundary. So now instead of having two regions connected by wormhole, we can think about more than one region. Let's say three regions, they are connected to each other. And then that represents, in terms of a quantum state, if the wormhole represent the maximal entangled space, state, or EPR state, now we have some sort of generalization of EPR pairs for more than two parties, let's say three parties, and so forth. Okay, so this type of thinking is not exactly necessary for my talk, but just to represent some intuitive line of thinking. So, and then once we get some sort of multi-parted entanglement, now we can reverse the arrow of the logic, then one can start thinking, oh, wait, we can actually use multi-party entangled state to define some sort of entanglement. That's sort of inner product. Okay, so now we can feed states. Okay, I have three regions. It's a multi-boundary geometry, but we can start feeding states into these regions, and then one can think of this as some sort of definition of inner product, but in fact this is now a generalized one because now have more than three states. So this is a generalized in that sense. We call it the multi-inner product. And I will mostly focus on the case with 3 parties, so it's a triple inner product. Okay, so the goal of this talk is to properly introduce this triple inner product in the context of many-body physics, and then we'll try to do something useful with it. Okay, a question?
Yeah, so in CFT we have operator state correspondence. So
Yes.
instead of calling this a triple inner product, is it the same as saying that it's a 3-point function?
Yeah, so that will show up, of course. Yeah, so we will first explore this idea in a critical system conformal field theory, of course. And then I will also talk about gap systems in 1 dimensions. And then I think thinking of in terms of the balance of the time, perhaps I will use this quantum critical system as a kind of another introduction. And then later part, I will focus on the gapped quantum state in high dimensions. As it turns out, this triple inner product, it is related to something which has been discussed also in this community, something called higher Berry phase. Okay? Then there's also something very closely related to this line of thinking, which is just study, not the inner product aspect, but just the multipartite entanglement in quantum many-body systems, such as topologically ordered phases. So we have some paper on this, so I want to acknowledge my collaborators here too. Okay, so this is the organization. So let me now jump into the first part. So in some sense, once again, I'm discussing various systems, but I'm using this multi-inner product as a lens or tool to understand the behavior of complicated many-body quantum systems. So here's a kind of quick numerical perspective. So for example, if I want to know something about one-dimensional many-body systems, we can ask, is it gap or is it gapless? And then, for example, if it is gapless, it can be described by a conformal field theory. And then one may want to know which conformal field theory is describing this critical point. So we want to know basically through information, through set of data characterizing conformal field theories. And then we saw that we can extract a central charge by looking at entanglement entropy scaling, for example. That's quite standard. And then we can also look at the spectrum of the Hamiltonian or maybe reduced density matrix. And then we can look at the spectrum, so to speak, the tau state, how it comes. And then we can get some idea of the underlying conformal field series. But these tools may not be enough to fully nail down the underlying conformal field series. So in principle, we may want to have more tools, okay? And I want to present one example where we have some lattice model which look like a critical, but we don't know exactly what the conformal field theory is, okay? So we are developing some sort of tool, okay? So now the tool we are interested in now is associate this multi-inner product. So in this 1+1d, 1D spin chain context, it is simply defined as follows. So I consider a eigenstate of one spin chain, let's say this purple spin chain with periodic boundary condition. So I get some state, okay? But then I also look at the state of different chains, same Hamiltonian, but with different lengths. So they are represented by these blue and red dots. So they have 3 spin chains. And then I look at the eigenstate of these spin chains, okay? And then I simply take overlap between these 3 states, so which can be, once again, defined in terms of some maximally entangled state for 3 parties, or in this case, I can just simply contract indices for the first part of the physical index for the first chain with the part of index of the second and third chain. Okay, so that defines this multi-wave function overlap, which is now written as A alpha beta gamma. One can also develop a space-time picture as before, but this case is just a path integral picture where I have a time evolution which is described by this Hamiltonian, so it's usually drawn as a cylinder. But now I'm feeding two states from the bottom, and there's the another state waiting at the top of this diagram. Okay, so this is the definition of the inner product. So this has been, came up as a kind of interesting object, and then this was first used by my collaborator Adrian, and they also Giffray et al. In this paper in 2021. So one can ask what kind of information we can get from here, and then as already anticipated, this will extract the interesting information related to three-point function. Question?
Yeah, so kind of going back to your previous slide, so from the conformal field theory point of view, so if you're actually looking at that we can get information about the central charge, but then we can also measure different correlation function and we can take the scaling and then extract the critical exponent.
Yeah.
So is that related to the next slide? So you're looking at some kind of correlation and then trying to find out some scaling and doing some...
It's related. So it's related. In fact, it shows up in the next slide. So we can relate this amplitude to the three-point function bias by state operator mapping. So of course, in conformal field theories, using the language of correlation functions, we want to predict all correlation functions. And then this is the kind of interesting way of, convenient way of doing it. Okay, so in particular, I guess it's like a question of why do we use entanglement to study the properties of the quantum spin chain, such as central charge. Are there other convenient methods to do it? I think this is kind of convenient one because, for example, you want to know exactly what is the eigen operator in conformal fields, so to speak, primary operators. But with this method, we can just get it from the spectrum, and then we just take an overlap to compute this three-point function. So, and Zhou and Vidal, they looked at this object, and then they related to the three-point function, and then to something called operator product expansion coefficient. So that's great too, because although we can measure correlation functions in numerics, let's say, this is a very convenient way to extract the data which wasn't captured by entanglement entropy scaling, nor just looking at the spectrum of the conformal field theory. So in the newer paper, we looked at the oh yes. Good.
So the ultraviolet part is entirely contained in that finite size expression. It doesn't have some exponential decay on top of it or something.
In the first formula, both formula.
Cancels in the first, but in the
Yeah, exactly. Yeah, that's right. So in the second, yeah, exactly. So in the first part, this geometrical factor, because I took the ratio, they sort of cancel out. And then in the second example where we looked at the finite size correction to this three-point inner product, then we will see the dependence on the length of the chain. And then we can also take a ratio, but this even with this ratio, this size dependence remains in the. So let's say for the ratio, there's also the corrections. Okay, and then we looked at this good question.
The Jacobian is just
Some factor like a 2 to power delta or something like that. So that is computed. It is similar factor also appears here. Yes. Okay. So so some details I don't think I have a time to tell you, but basically we figured out this formula. So now this is something we can also use to test to obtain extract the conformal data. Okay. Oh, sorry. Yeah. Yeah.
A quick question. So one of the most important consistency conditions satisfied by the three-point function is crossing symmetry.
Yes.
And
That's an interesting question. I don't have the answer off the top of my head, but we can, yeah, we can talk about that later. Yeah. Okay, so this type of method is useful once again if I have some lattice system for which we know it's conformal, or we are just convinced it's conformal, but then we may want to know more details. So I just just flash one example here. That is the interesting, so to speak, anion chain studied by these people. So interestingly, they found a conformal field theory, evidence of conformal symmetry in this chain, but the precise nature of the conformal field theory has not been identified yet. So we could use our methods to test a possible candidate of conformal field theories, and then so far we get some negative results for the predicted candidate. But that's to show you the power of this method. Okay. Since I also want to talk about gapped state, let me move on to the gapped state. So once again, we kind of introducing a generalized version of inner product, and then if you have a inner product, you can study two things: the amplitude and also the phase. And the phase part is the very phase. So in the previous part, it's more like the amplitude part, in particular the scaling of the amplitude part. But now I'm also interested in the phase part of this inner product, and then the best stage for this is to study gapped quantum state, because we are talking about the very phase. And then we are now interested in the gapped phases in 1 dimensions. And then is there interesting very phase associated to this inner product? Okay? Then, as it turns out, this phase I'm talking about is related to, or in fact it is, the higher very phase discussed in many literature, and there's a lot of papers appearing on this paper, on this subject, so I apologize if I don't list all of them, but here's some references. Okay. So before discussing the higher Berry phase, let me briefly mention something about Berry phase. So in the Berry phase, a typical setting is that I have a parameterized state which changes adiabatically as I change parameter, let's say x. Okay? And then we can sort of define a gauge field or Berry connection, and then that's really associated to the gauge transformation or phase ambiguity of the quantum state. So you can change your state by multiplying a phase. It doesn't change the physical state. Okay? I would also like to mention some mathematical framework, which is this fiber bundle theory. So that is behind this Berry phase or just gauge theory discussion. And then for many of condensed matter physicists, most interesting setting is the setting with monopole. For example, this shows up in the Chan insulator. So I have a parameter space, but parameter space, well, let's say inside this parameter space, there may be some monopole, which is the gap closing point. And then if that happens, you cannot fully cover the parameter space by single gauge, so your wave function has to be defined by patch. And then when these two patch overlaps, we have to have a transition function relating these two wave functions. And then that's how we describe a monopole, and then that is classified by Chan number or Chan class. Okay? So that's basically the, from physicist's point of view, this is a Wu-Yan's description of magnetic monopole. So now we want to generalize it. So I have now a parameterized gapped state, and then I'm going to use this matrix product state as a very convenient way to describe a gapped state, or short-range entangled or invertible state in 1+1 dimensions. So I have a family of matrix product state, which depends on the parameter. It is known that there's the kind of redundancy akin to the phase redundancy of quantum state in the context of matrix product state. So I just call it a matrix product state gauge transformation. So I have tensors forming matrix product state, but I can sandwich this tensor by two G and G dagger. That won't change the physically the matrix product state because these operations cancel in the mid bonds. So this is the gauge transformation, which does not exist in the single particle quantum mechanics. It is truly exists because of this tensor product representation of the quantum state. So one may wonder, is there any way I can get something like a Bayer phase associated to this phase redundancy? And then, not phase, but MPS gauge transformation. So that is the kind of the motivation for this, use the triple inner product. And then try to relate it to this concept of generalized version of Bayer phase. Okay, so here's the, I'm just flashing some main results. So I have one more slide to discuss some more details, but here's the summary of the results. So we introduced the triple inner product for 3 matrix product states, and we computed this inner product for some cases. And then, as it turns out, the just like the inner product for the case of a quantum mechanics example I described, just like this inner product detect the Chern number or Chern class for the case of monopole, we were able to relate this triple intersection to the something similar to the Chern class, but in this case it is known as the name of a Dixima-Dardy class. So that's kind of mathematical object which classify a generalized version of 5 of under. That is called GERV, but I don't know about GERV, so I do not present this GERV. But the way we make this connection is that we consider the family of matrix product state, and then we kind of try to fit this description into the mathematical description of GERV. And just like we can fit the Bayer phase description of Bayer phase into the description of 5 of Vandel, and then we can identify this triple intersection as a something which is related to the classification of this GERV. Okay, but anyway, that is kind of a mathematical background. What I want to just demonstrate now is that how triple inner product actually capture the MPS gauge transformation. So let me just flash the idea here. So if you look at this inner product here, it has once again the structure where part of the state is glued to the other part, part of the other state, and so on and so forth. So we don't take a full overlap. Okay, and then this is a matrix product state. So if you're just locally looking at this part, it is really like the inner product of the 2 matrix product state. But then somehow there's this branching structure, so that defines this triple intersection. If we want to know something about inner product in matrix product state language, there's a very convenient way of computing the inner product using the transfer matrix. Okay, so basically we look at this direction as a time, fictitious time, and then when you try to compute the inner product, we can multiply this transfer matrix in many times, and then there are some states survives in this process which basically capture the inner product of the state. Now we have a 2 state, which I call alpha and beta. So these are 2 matrix product states. They are parameterized, and then they are so to speak, they live in a different patch. Just like we have the North Pole and the South Pole patch for the case of monopole. So we have a transfer matrix now for 2 different matrix product states. And then we basically repeat the procedure I just said for the calculation of inner product. So I first look at the kind of fixed point of this transfer matrix, which we can actually easily compute. And then knowing this eigenvector or fixed point, we can basically reduce the entire calculation to the inner product or this object, which is the trace of these 3 eigenvectors. And then this eigenvectors for this mixed transfer matrix for two matrix product states, they capture, in fact, the this object G, which appears in the MPS gauge transformation. So that's a kind of short description how this inner product actually capture the MPS gauge transformation, and it captures this particular combination. Okay. And then I just want to say a few words about what is the use of this. I kind of focused on the tool development, and of course, this higher Berry phase has been discussed in the context of a adiabatic, something like adiabatic process. So for the regular Berry phase, we have a famous Saurus pump. You have a family of, let's say, fermionic system band insulator, which depends on the parameter, and then as you change a parameter, you can pump a unit charge or integer unit of charge during this process. So associated this higher Berry phase, there's the generalization of Saurus pumping, which is usually known under the name of higher Saurus pump. So we can apply our method to this some concrete model, which was discussed by these people here. We did something on this calculation, but I want to also introduce another great paper from these people, which more seriously did this, so to speak, more seriously did this calculation of higher Berry connection. So some details aside, if you closely follow what I said, I didn't say anything about the Berry connection for higher Berry phase. I'm entirely focused on what happens along the patch. That is the description of Uyan monopole, and I did somewhat generalized version of it. But we could also discuss what is the Berry connection along this line, and in this paper, they study the Berry connection, and they actually compute the topological invariant of the higher Saurus pump. Okay, so these are great works. Just for last 2-3 minutes, so the kind of conclusion is that matrix product state, it can couple to higher Berry, maybe couple to is not the correct word, but matrix product states are somewhat associated to form a gauge field or higher Berry field. And then usual particle, it only couples to U1 gauge field, one form U1 gauge field, and there's the Aharonov-Bohm effect, which can be understood as the regular Berry phase. Of course, here we are talking about not the fundamental particles, but some emergent state. And then this really behaves as the extended object. That's why we have an internal structure, and that's why we can couple this MPS to somewhat more complicated gauge field than regular one-form gauge field. Okay, so this looks very similar to what people do in string theory, in fact. But of course, in string theory, we may have a fundamental strings, but in condensed matter, we have emergent strings. So they couples to this higher Berry phase. There's an interesting formal connection we found with, in fact, the string theory. So in this paper, they discussed the something called the string field theory, where they try to define the interaction between strings. And then, as you can see, diagrams in this paper is actually very similar. Okay, so 3 strings meet, and then they interact with each other. And in fact, we can really phrase our construction of inner product using this language, which perhaps I don't have a time, so I don't go through. But ingredients presented in this paper is the generalized product, not inner product, but the generalized product of 3 states. There's also something called integration, which contract 2 strings. But they are really fit into this description we are having for the multi-inner product. So I have a matrix product state. So in our language, I can define a product of two matrix product state by first bending this matrix product state. Let's say here, so I split this matrix product state into left and right and bend, and then partially contract. Okay, essentially I'm doing something like a reduced density matrix calculation. And then I can also bend this thing here in the middle, and then I close up this whole matrix product state. That is a way to get inner product out of matrix product state. And then combining these two operations, I can write the triple inner product as a product of this star product defined here, and then the final integration, which is nothing but this triple inner product. So since the lunch is waiting us, so let me stop here, and then I just want to thank my collaborators. Thank you very much for your attention.
Yeah, thanks a lot for the interesting talk. Maybe I have a question from the slide that you mentioned about the calculating the central charge from this triple inner product for the model of a anion model that you had or some. Yeah, so when you said that this is not like recovering the results that was reported before, does that mean those results are theoretical or it's hard to calculate?
Yeah, so sorry, I didn't say much about it. So, these people constructed the anion chain and they studied the spectrum numerically. And then they found, it's numerics, but there's a very good evidence that this system is at a conformal critical point. Mm-hmm. But then they get all spectrum, and then they can start to see how we pack this into conformal field theory language. Extracted central charge is very close to 2, and then at this value we may have a lot of candidates. Mm-hmm. They proposed one possible candidate, and then in particular in this paper. So in that candidate description, they predicted some spin 1 state, and then we took this proposal, and then we kind of ask ourselves what could we test using our technique. So that's what is plotted here. So we compare this with expected value, this ratio, but numerically we get something different. That's the only thing we could say now.
But then maybe a related question would be, would this value would be also consistent with the value that you would get with the entanglement triple, or wouldn't?
Yes, good question. So we can also extract central charge, and it's very close to 2, so not exactly the same, but I don't know error bar and so on and so forth. So they are largely consistent, but of course it may not exactly 2. That's numerical. It may not be exactly 2, but it's very close to 2.
All right, thank you.
I wasn't quite sure about the slide with the triple product with the MPS.
Uh-huh.
Where do you really need the MPS structure to define this? Seems like you're just contracting these 3-way functions.
Yeah, we may not need this. So we didn't write our paper that way, but in fact, matrix product tensor is really, something closely related to the Schmidt decomposition of the state. So in practice, we may not need it in general, and then it may be even better that way because we don't have to rely on particular tensor network.
No, but
if the partial need to conjugate half of one state.
That's part maybe that part so one. Okay, so the one convenient technical part is that if you look at this part, maybe I didn't, I'm pretty sure I did not explain that. But this part is bra, this part, dotted part is a cat, so it's conjugated. But this part has a part of it is a cat, and part is bra. So that is very easy to get by MPS. If we want to get something like that, we first need to start from 2 states, and we, do partial trace, and we can still represent this as the reduced density matrix. But there's certainly some convenience there to use the matrix product state.
And the second question is, how is this related to the pants pictures you were drawing earlier? Is there any relation?
Sorry. Yeah, I kind of anticipated that this picture may not look like a pants diagram at all. Yes, but this is a gapped state. So since it's a gapped state, you can sort of shrink this region quite a lot. It's a trivial time evolution. So you just shrink this all the way when these three regions meet. So that's how I'm thinking about it. In conformal field theory, there are a lot more dynamics, so that's why we get this Jacobian, something like that. But in gapped state, what's happening here should be something relatively simple, not entirely simple.
But here you don't need this partial transpose, right?
Yeah, so the question is, so we can do, looking at this picture, you can do various ways. You can first take, so in the first picture, maybe we can talk this more along branch, but here I'm just taking this as a bra, ket. So I don't have to split this into I don't have to split particular state into two regions. But looking at this picture, this is meant to be introduction, so there are many ways we can develop from here. Okay.
It's a vague question, but I'm wondering if you think the large bond dimension limits of the MPS you're thinking in this context, if that is interesting or not.
It may play an important role. It has been recognized that if you limit the number of bond dimension to be finite, you want to be able to describe certain type of higher tau response. And then, of course, people study this triple inner product or some version of it numerically. They do DMRG. So depending on the error you choose, it's not strictly infinite because you have to truncate, but it's very large. So we have to have a formulation which can accommodate such flexibility of the bond dimensions.
I see. I'm asking because you mentioned that there is a kind of gauge symmetry associated to the bonds between the sides of the degrees of freedom. So that's the reason why I was asking that.
Yeah, exactly. So that's precisely a very important aspect.
Thank you so much.
One more question. Matt? We're a little bit late for lunch.
So on the very first slide, you showed how to contract with the Bell pair. I'm just wondering what the three-body version of this is. Do you contract with like a GHZ state or a W state or something like that?
So simplest version, we have to do this with W type state or properly defined W type state, properly defined by Micron companies. It's called sum of triangular state.
Mm-hmm. I'm just confused how. Because for MPS, you have to glue stuff together, but here you don't really have to glue different. Is there a nice way to see the relation?
So gluing like gluing this way?
Oh, for the MPS, you have to glue like one part to one.
Yes. So it's somewhat similar question here. So there may be tiny difference, but easiest could be just take a tripartite entangled state and feed all bras. Sorry, or cats. I always confuse the cat and bra, but just feed bras. Then that defines one version that may have. So here's the version I'm using. Okay, but in this description, I also kind of secretly mix two conventions where I take two bras and one cat, and then for the gapped case, I have yet another version. So sorry for the confusion, but we have some freedom or flexibility to choose here.